Imagine that you're tossing a coin, and while it's spinning in the air, is both heads and tails at the same time. Not only do we not know what will fall out, but it really exists in both states at once until it falls on the table. Sounds crazy, right? But this is exactly how quantum objects behave: electrons, atoms, photons. They can be here and there at the same time, rotating clockwise and counterclockwise at the same moment. This is called superposition, and it is not science fiction, but an experimentally confirmed fact. But then the obvious question arises: if everything works so strangely in the microcosm, why don't we see it around us? Why is your cat either alive or dead, and not in a superposition of these states? Why is the chair in the corner of the room and not smeared by a probabilistic cloud all over the apartment? Erwin Schrödinger came up with his famous cat thought experiment precisely to show the absurdity of transferring quantum rules to ordinary objects. But the paradox remains. The laws of quantum mechanics are universal. They apply everywhere. So why does the macrocosm look so classical, definite, and unambiguous? The answer lies in a phenomenon that physicists call decoherence. This is the process by which a quantum system loses its magical quantum properties due to interaction with its environment. And this interaction occurs constantly, continuously, inevitably. Every atom in your body is bombarded by photons of light, air molecules, thermal vibrations. Each such collision is a dimension that pulls the system out of superposition into one specific state. Think of it as a secret that cannot be kept. Quantum superposition is an incredibly fragile thing that requires absolute isolation. But in the real world, there is no absolute isolation. Think of a quantum state as a perfectly tuned musical instrument playing a complex melody. And the environment is a crowd of people who constantly touch the strings, knock on the body, breathe on it. Very quickly, all this fine-tuning turns into a cacophony, and then into the silence of an ordinary classical object. The most striking thing about decoherence is its speed. For microscopic objects in a vacuum at low temperatures, superposition can exist for quite a long time, maybe milliseconds or even seconds if you try very hard. But for something the size of at least a speck of dust under normal conditions, decoherence occurs in a time of about 10 to minus 20th of a second. It's so fast that our brains can't even imagine it. Faster than light travels a distance equal to the size of an atom. During this time, any quantum superposition of a macroscopic object collapses into one definite classical state. Why is size so important? It's about the number of interactions. A single atom can collide with multiple photons per second, but an object of a billion atoms interacts with the environment billions of times per second. Every atom on the surface of this object is a potential point of quantum information leakage to the environment. Information about the state of the system is distributed to the outside world through these countless interactions, and there is no turning back. It's like trying to collect the smoke from a cigarette. Theoretically possible, almost impossible. Physicists have long debated what actually happens in quantum measurement. The Copenhagen interpretation spoke of the mysterious collapse of the wave function, but did not explain its mechanism. The many-worlds interpretation proposed a branching of reality into parallel universes. But the theory of decoherence has shown that there is no need for any mystical collapse. It is enough to take into account the interaction with the environment, and quantum mechanics itself naturally gives rise to the classical world that we observe. The key word here is entanglement. When a quantum system interacts with its environment, it becomes entangled with it. Information about its state is encoded not only in itself, but also in the countless degrees of freedom of the surrounding particles. If you had an isolated photon in a superposition of horizontal and vertical polarization, it has distinct quantum properties. But as soon as it interacts with a molecule of air, now the information about its polarization is smeared between the photon and the molecule. With one more molecule, it is even more smeared. In a moment, this information has spread to trillions of particles, and it is almost impossible to recover it. This explains why we never see quantum superposition in everyday life, but it also poses huge problems for quantum computers. Engineers spend billions of dollars to isolate qubits, quantum bits of information, from their environment. They are cooled almost to absolute zero, placed in a vacuum, shielded from electromagnetic fields. And still, decoherence wins in a fraction of a second. This is a race against time. You need to do all the calculations before quantum information leaks into the environment and is lost. Interestingly, decoherence explains not only why we can't see quantum effects, but also why we can see anything at all. When a photon of light bounces off an object and hits your eye, it carries information about the position and state of that object. This interaction is decoherence. The photon measures the object, pulling it into a certain classical state. Without decoherence, the world would be a nebulous ocean of quantum probabilities, where nothing definite could be distinguished. There is another surprising aspect. Decoherence is irreversible, and this is closely related to the second law of thermodynamics and the arrow of time. When quantum information is scattered into the environment, the entropy of the system increases. To collect this information back would be to violate the second law of thermodynamics, which is impossible in an isolated system. So in a sense, decoherence is the quantum embodiment of the irreversibility of time, the explanation of why the past is different from the future, even at the quantum level. But the most philosophically profound consequence of decoherence is the understanding that the classical world does not exist in parallel with the quantum world. The classical world is an approximation that arises from the quantum world in the presence of the environment. The very definite properties of objects that seem so obvious to us, position, velocity, shape, are not fundamental characteristics of reality, but the result of constant decoherence. Without interaction with the environment, these properties are blurred into quantum uncertainty. Scientists have learned to use the understanding of decoherence to create increasingly sophisticated experiments. They learned how to create mesoscopic systems, not exactly microscopic, but not macroscopic either, where you can observe the boundary between the quantum and classical worlds. Molecules of hundreds of atoms in interferometric experiments, superconducting circuits with currents of billions of electrons, exhibiting quantum behavior. This is a test of how large an object can be if it still exhibits quantum properties, can be if it is isolated from its surroundings as much as possible. Imagine a concert hall with perfect acoustics. One musician can play the most delicate melody, and you will hear every note. But open the doors, let in the noise of the street, add the conversations of the audience, the echo from the walls, and the melody will dissolve into a cacophony. Quantum superposition is that subtle melody, and decoherence is all the noise that drowns it out. We live in a world where the doors are always open, where cacophony rules the roost, and only in specially created concert halls of laboratories can we hear quantum music for a short time. There are even hypotheses that consciousness may be related to how the brain handles decoherence. Maybe some processes in neurons or microtubules inside cells are partially protected from decoherence and can use quantum effects. It's a controversial idea, and most physicists are skeptical of it because the brain is a warm, moist, noisy environment where decoherence must happen incredibly quickly. But the very fact that such questions are being asked shows how profoundly our understanding of decoherence changes our understanding of the boundary between the quantum and classical worlds. Decoherence also helps to understand why classical physics works so well for ordinary objects. This is not because it is fundamentally true, but because it is an excellent approximation for systems that are constantly undergoing decoherence. Quantum mechanics in the limit of fast decoherence gives classical mechanics. This is a kind of quantum Darwinism. Only those states that are stable in relation to interaction with the environment survive, and these are classical states with certain positions and impulses. So when you look at the world around you, the walls, the trees, the people, you are not seeing the true quantum reality, but a projection of it, filtered through countless interactions with the environment. This does not mean that the world is illusory, but it does mean that its classical certainty is not a fundamental property, but an emergent one that arises from a deeper quantum level. We don't see quantum effects in a macrocosm because the environment is continuously measuring everything around us, collapsing superpositions faster than we could blink. And this is perhaps the only reason why the world looks so stable and predictable that in a sense, each of us is a decoherence tool. When you look at an object, you don't just passively receive information. Photons bouncing off an object and hitting your retina physically alter its quantum state. Every act of observation is an interference with quantum reality. Ancient philosophers argued about whether a tree exists in a forest if no one sees it. From the point of view of quantum mechanics, without observers and interactions, the tree would exist in some vague cloud of probabilities. But thanks to the constant bombardment of photons by sunlight, air molecules, and the rest of the environment, it is continuously measured and therefore exists as a classical object, even when no one is looking at it. The decoherence time depends not only on the size of the object, but also on how strongly it is connected to the environment. An electron in a vacuum can maintain a superposition for quite a long time. The same electron in a piece of metal loses it almost instantaneously because it is constantly interacting with trillions of other electrons around it. This explains why quantum computers are built on the basis of isolated ions in traps or superconductors at temperatures close to absolute zero. The fewer interactions, the longer the quantum information lives. But there are systems that surprisingly resist decoherence, even in a warm and noisy environment. Photosynthesis is one such example. When a plant absorbs a photon of light, the energy must travel through a complex system of molecules to the reaction center. For a long time, it was thought that this was a purely classical process, but experiments have shown that energy moves like a quantum wave, trying all possible paths at the same time and choosing the most efficient one. This happens at room temperature in a liquid medium where decoherence should kill any quantum effects in femtoseconds. How nature managed to protect this quantum coherence is one of the great mysteries of modern biophysics. Perhaps evolution has learned to use decoherence rather than just fight it. There is a hypothesis that the structure of proteins in photosynthetic complexes creates an environment where certain quantum superpositions are protected and others quickly decohere. This is a kind of quantum filter that weeds out inefficient paths and preserves useful ones. If this is true, then life has found a way to dance on the border between the quantum and classical worlds, using the best of both. There are even stranger ideas. Some physicists suggest that gravity itself can cause decoherence. According to general relativity, mass curves spacetime, but the quantum superposition of a massive object would mean that spacetime is curved in two different configurations at the same time. Perhaps the very structure of spacetime does not allow for such superpositions and automatically collapses them. This is called gravitational decoherence or objective collapse. And if true, quantum uncertainty has a fundamental limit to gravity. An object heavier than a certain mass simply cannot be in a superposition of positions, because that would contradict the structure of spacetime. These ideas are still speculative, but they show that decoherence is not just a technical effect, but a window into the deepest questions about the nature of reality. Why is the world quantum on small scales, but classical on large scales? Is it a fundamental feature of the universe? Or is it an accident that we live in an environment with high temperature and density? If the universe were colder and more rarefied, could macroscopic objects exhibit quantum behavior? In the early universe, just after the Big Bang, the temperature was incredibly high, but so was the density. Decoherence was monstrously fast. But there were brief moments in the history of the cosmos when the universe expanded so rapidly that particles lost their connection to each other. At these moments, quantum fluctuations could grow to cosmic scales without decohering. It was these quantum fluctuations, stretched by inflation to the size of galaxies and preserved from decoherence due to the expansion of space, that created those inhomogeneities for which all the structures in the universe were later formed: galaxies, stars, planets, you and me. So in a sense, all we see around us are fossilized quantum fluctuations that escaped from decoherence thanks to cosmic inflation. Think about it. The structure of the Milky Way, the position of the Sun, the existence of the Earth are all traces of quantum uncertainty that miraculously survived long enough to become a classical reality. We literally live inside a fossilized quantum superposition. If decoherence had worked faster in the early universe, these fluctuations would have smoothed out and the universe would have been perfectly homogeneous with no stars or galaxies. So our existence depends on a delicate balance between quantum uncertainty and decoherence. In the labs, scientists are creating increasingly impressive demonstrations of quantum superposition with large objects. Recently, it was possible to show the interference of molecules containing more than 2,000 atoms. These are objects that can almost be seen through a microscope. They were in a superposition of two trajectories at the same time, and this superposition was maintained long enough to see the interference pattern. But the experiment required a deep vacuum and careful control of all sources of decoherence. The slightest collision with a molecule of residual gas and quantum behavior disappeared. There's something deeply ironic about the fact that the more we learn about an object, the less it behaves quantumly. Information and quantumness are antagonistic to each other. Quantum superposition is a state of maximum uncertainty when information about the system is minimal. As soon as information begins to leak into the environment through interactions, the superposition collapses. We can say that the classical world is a world of maximum information, where everything is constantly measured by everything, and the quantum world is a world protected from the flow of information, where true uncertainty is possible. This explains the Friend-Wigner paradox, an extended version of Schrödinger's cat paradox. Imagine that your friend is conducting a quantum experiment inside an isolated laboratory. For a friend, the wave function collapses when he sees the result. But for you, outside, until you have information about the result, the entire laboratory, including the friend and his measurement, is in a superposition. The paradox is resolved when you realize that the friend has been decoherent with the environment of the laboratory, with the air, the walls, the equipment, and therefore there is a certain result for him. Even if for you, who have no information, the system is still quantum. But as soon as the photon of light that carries information about the result comes out of the laboratory, you also decoherent with this system, and the result will also become certain for you. Interestingly, decoherence creates the illusion of the classical world, but does not completely destroy quantum information. Information still exists, it's just scattered across the myriad degrees of freedom of the environment. In theory, if you could track every particle in the environment and reverse the evolution of the system, you would regain the original superposition. But this would require controlling an exponentially large number of variables. For an object the size of a grain of sand, you would have to track and control every photon, every air molecule, every quantum fluctuation of the vacuum that interacted with it. Not only is this technically impossible, it requires resources that exceed the energy content of the observable universe. So decoherence is not a violation of quantum mechanics, but a practical irreversibility that arises from complexity. Quantum information does not disappear. It simply becomes inaccessible, buried in the correlates between the system and the astronomical number of degrees of freedom of the environment. It's like a drop of ink that falls into the ocean doesn't disappear, but simply dissipates so that it can't be put back together. There is a beautiful mathematical formulation of this process through the so-called density matrix. A pure quantum state is described by a wave function, but a system entangled with the environment is described by a density matrix that contains only the information that is available to an observer who does not have access to the environment. Decoherence is a process in which the non-diagonal elements of this matrix, which are responsible for quantum interferences, are exponentially rapidly approaching zero. Only the diagonal elements remain, the classical probabilities of the system being in certain states. There is also the concept of decoherence pointers. These are the states of a quantum system that are most resistant to interaction with the environment. For a particle in space, the pointers are usually states with a certain position, so objects appear to us to be localized in space. For the spin of a particle in a magnetic field, the pointers are states with a certain spin projection on the direction of the field. The environment chooses those basic states in which the system appears classical, and this choice depends on the nature of the system's interaction with the environment. This explains why we see the world in a certain way. We don't just see the world, we see it through the lens of decoherence caused by a particular type of interaction. If photons interacted with matter differently, we would see other aspects of reality as classical. Our perception of the classical world is not an objective given, but the result of a specific decoherence mechanism inherent in our type of measurements. This raises a dizzying question. Are there other classical worlds carved out of quantum reality by other decoherence mechanisms? Perhaps somewhere in the universe, there are beings who interact with their surroundings in such a specific way that the momentum of the particles seems classical to them, rather than their positions. They would live in a world of certain speeds, but blurry locations, the exact opposite of our experience. Or creatures for whom decoherence is indicated by the phases of wave functions living in a world organized around interference patterns. This is pure speculation, but it shows how much our perception of the obvious classical reality depends on the accidental details of our physical embodiment. Ultimately, decoherence teaches us humility. A world that seems so solid, so definite, so obvious is just one way of looking at quantum reality, a way that is forced upon us by our interaction with our environment. An ocean of quantum probabilities boils beneath this classical surface, but we can't see it because we are so deeply immersed in it that we ourselves have become part of the mechanism that creates the classical world. We are decoherence agents, going around the world and collapsing wave functions simply by the fact of our existence, without even knowing it. And yet, despite all this inexorable decoherence, the quantum world is not disappearing completely. It just hides in the cracks between the interactions, in the fleeting moments of isolation, in the cold of the cosmic void. Every electron in your brain, every photon of sunlight, remains a quantum object, even if its quantum properties are masked by constant collisions with the environment. Quantum mechanics doesn't cancel on large scales. It just becomes so entangled with its surroundings that it looks classical. Perhaps the most profound lesson of decoherence is that the boundary between the observer and the observed is an illusion. We do not stand outside of nature, measuring it from the outside. We are part of a giant quantum system that is constantly entangled with itself, creating the appearance of independent objects and observers through decoherence. Each act of perception is not a passive receipt of information, but a physical process in which the boundary between I and world is blurred at the quantum level. When you look at the stars, the photons that have traveled through the cosmic void for millions of years, maintaining their quantum coherence, finally decoherent with the atoms of your retina, turning potentiality into reality, wave into particle, possibility into fact. So yes, we don't see quantum effects in the macrocosm because we live in a warm, dense, noisy corner of the universe where decoherence triumphs at every turn. But that doesn't make the quantum world any less real or less important. This makes us classical beings that arose from a quantum substrate, something like standing waves on the surface of a quantum ocean. We exist because decoherence has created stable classical structures. But at the heart of our being is the same quantum uncertainty that we never see directly. And maybe there is some poetry in it. We are children of the quantum world that we cannot see, the creation of superpositions that we cannot feel. We are made of the same matter that demonstrates the wonders of quantum interference in the vacuum of laboratories. But in us, these miracles are crushed by the endless noise of interactions. We are classic beings, forever cut off from the direct perception of the quantum reality that gave birth to us. But through mathematics, experiments, and understanding of decoherence, we still touch this hidden reality, realizing that the world is much stranger and more beautiful than it seems to our senses. Decoherence is not just a technical term from quantum mechanics. This is the story of how possibility becomes reality, how uncertainty turns into certainty, how the quantum world gives rise to the classical world. This is an explanation of why the universe did not freeze in a state of endless quantum confusion, but crystallized into a world of objects, events, causes, and effects. It is a bridge between two realities, quantum and classical, and we stand on this bridge without knowing it every second of our lives. The environment is constantly measuring us. We are constantly measuring it. And in this endless dance of mutual decoherence, the world we call reality is born.